All right, top of the evening to everybody. Uh, in this class, we have quite a number of questions to answer, and I really hope we can move as fast as we can, although ensuring that we can all follow through with all of the solutions. So we have some beautiful questions we have to resolve this night, ranging from several topics under A-level mathematics. We're going to be starting the night with a question on sequences and series. And I would love you to pay real attention to this particular question because this is right from a past question. And I want you to really pay attention so that you can be able to solve questions like this. All right, here is the question. We have the sum of the first n term of a geometric series is 127, and the sum of their reciprocal is 127 divided by 64. If the first term is 1, find n and the common ratio. Now, this is quite a very interesting question. Let's study this question carefully so we can move with the right steps to solve it. The very first detail that was given us is that the sum of the first n term of pay attention to the word here, a geometric series. All right. The very first thing is a geometric series. And then we're dealing with the sum of the very first n term, the first n term of a geometric series. And we're told that that sum is given by 127. All right. Now, the next detail is that the sum of their reciprocal, just in case you don't understand what that meant, is saying, imagine for instance, this was the geometric series, of course, on and on and on. Imagine this was the initial geometric series of which the sum was 127. The next detail is saying the sum of their reciprocal. That means reciprocal now will be 1 over 2, 1 over 4, 1 over 8, 1 over 16. All right. So this is the meaning of that. So what we're told here is that the sum of the very first n term, we are not told the number of terms. I want you to take note of that also. And we were not told the number of terms of which sum gave us 127. But we just told that there was a particular number of terms of which the sum gave us 127 when we're dealing with a geometric series. Now, when we went on to do the reciprocal, We're then told that the sum of their reciprocal, of course, the same n term, gave us 127 over 64. The next detail we're told here is that the first term, that means our A value, is 1. All right, that's a very good information because that's always pivotal to solving questions once we know the A. So we're told that the very first term is given as 1. Now, we're told to find n, which is the number of terms. That means what was the number of terms that were added to give us a total of 127. And then the next term said we should find the common ratio, the R value. All right. So this is the very first challenge in front of us for this night. We have to find a way to resolve this. I'm sure you guys are ready for a great time this night. We have a couple of questions to solve. So the very first thing I would ask you to first note is that the very first detail that was given was that the sum of the first n term of a geometric series. Remember when we were discussing sequence and series, I explained to you guys that it's very important to note all these formulas as they are very key in solving questions. Of course, in this particular situation, we're going to have to bring back our sum of the first n term of a geometric series. And I'm sure we all agree, if I write it this way, that the sum of the n term is given as A times Rn minus 1 over R minus 1. I'm sure we all remember this. This is the sum of the n term of a geometric series. Of course, I'm sure somebody out there will say, but we have another one which can be 1 minus Rn over 1 minus R. Whichever one you use, I submit to you that you're going to get the same thing. So it will work either way. All right. Now, let's start from here. Let's try to insert all our detail on this particular question. So the very first thing I know I'm giving is that I was told that my A value, I was told that A equals to 1. That's it right here. And I was also told that the sum of this n term, Sn, is what? 127. That's it given here. 127. All right. So, all right. It looks like our black marker is needing new ink. All right. So the very first thing you have to do is to substitute the value of. You have to substitute the value of Sn into this particular formula and substitute that of A also, of course, as 1, and then Sn will be giving you a value of 127. So what I can write now is 127 will be equals to 1 Rn minus 1, R raised to n minus 1 over R minus 1. Of course, it's okay if I wrote it as R raised to n minus 1 over R minus 1 equals to 127. All right. Okay, this was 127. Yeah, our black marker is still coming up. It will be done very soon. All right. So let's highlight this as our equation 1. What we have gotten here, let's highlight this as our equation 1. So right here, we have the first equation. So wherever you are, I want you to note this particular equation. We'll be calling it very soon. Now, what's the next thing I can do from here? I've been able to bring out my solution from the very first detail I was given. Now, the next detail I was given, let's try to tackle that. I was now told that the sum of their reciprocal, is what? 127 over 64. Now, pay attention to what I'm going to explain to you right here. This is still booting, right? You see, you need to really pay attention at this point because I want to bring you how you're going to solve for this sum of the reciprocal. Let's try and do something around what we did before. Let's have 2, 4, 8, 16, and so on. Let's try and get the reciprocal 1 over 2, 1 over 4, 1 over 8, 1 over 16, and so on. All right, good. Now, I want to show you some of the features of this reciprocal sequence. Now, number one, don't forget, I told you that the first term of the sequence was 1. Now, don't forget this was a dummy. So let's try and imagine we're dealing with the sequence here. If we're one thing in this particular sequence that gave us the sum of 127, one thing we are sure of is that the very first term is 1. We don't know the rest of the terms, but we know the very first term is 1. The reciprocal of 1 will always be 1 also. So I've been able to decode that for my reciprocal term, my A is still going to be 1 also. Of course, because the reciprocal of 1 will always give us 1. Let's note that. That's very important and vital. Now, the next thing you have to pay attention to is, let's talk about the common ratio. What's going to happen based on the common ratio? What's going to happen based on the common ratio? So I'm going to use this dummy to explain to you what happens when we're dealing with the common ratio. Notice something here. The common ratio in this particular first sequence, my R here was equals to 2. I'm sure we all agree with that. Now let's see what happens when we had the reciprocal. You'll notice that if you had a reciprocal sequence, the R was going to be what? 1 over 2. It was also the reciprocal of the common ratio. You can go on to find that out. 1 over 2 times 1 over 2 gives me 1 over 4. 1 over 4 times 1 over 2 gives me 1 over 8. 1 over 8 times 1 over 2 gives me 1 over 16. So you can see these particular features, you need to highlight them because they'll be very much needed for this next detail that we're giving. When we're told that the sum of their reciprocal is 127 over 64. So let's go on and use this particular place to highlight that. Now we are told that the sum of their reciprocal gave us 127. So how do we go about that? Of course, for this reciprocal term, let's use a R to talk about the reciprocal. Or do we have to do that? Yes, we can do that. Let's talk about the reciprocal. This was for the original sequence. Now for the reciprocal, let's say AR, that means the first term of the reciprocal sequence was 1. Now the common ratio, of course, here the common ratio was R. Here the common ratio, let's call it capital letter R, is equals to 1 over R. In this case, the common ratio was just R. The ratio was R in this particular first sequence. These are very important things you need to note. So let's now go on to try and solve this statement. The sum of the reciprocal is 127 over 64. What's that going to mean? Of course, if you look at the general sum, when we're dealing with general formula, when we're dealing with sum of terms, we have it given as this. So let's call this S n comma R, meaning the sum of the terms based on the reciprocal sequence. Now let's call it that. Of course, our A here will be 1 because A is, I already explained to you that the first term, the reciprocal of the first term will also be 1 because when you reciprocate 1, you're going to get 1. So we're going to have 1. Now our common ratio is no longer R here. For the reciprocal term, our common ratio is 1 over R. So we're going to be having 1 over R raised to power n minus 1. I'm sure you understand that. Over, we're no longer going to be having just R now. We're going to be having 1 over R minus 1. All right. Now, I'm sure you understand what I was doing, but don't forget, they told me already what the sum was. They told me that the sum was equals to what? 127 over 64. So I can go on, instead of writing Sn, I can go on to write this as 127 over 64. All right. Now, this is where I will tell you to ensure you note this particular sequence. Note what we have here, please. Just note this. We're going to be calling on this. I called it equation 1. So when I mention equation 1, remember this is what I meant. So I want to go on to solve this sum of terms for the reciprocal. I want to go on to work on this. Permit me to rub off the question. I believe we all have the question so that we can make use of this space. I believe we've taken all the details we actually wanted so that we can have enough space for solving. All right, now look carefully at what I'm going to do right here. I have 127 over 64 equals to, of course, 1 times that. So I can say 127 over 64 is equals to what? 1 over r raised to power n minus 1 over 1 over r minus 1. Does anybody feel I've done anything wrong in this particular scenario? No, not at all, because you can see what I just did was, in this case now, we have 1 over r everything raised to power n. Of course, this is equals to 1 raised to power n over r raised to power n, right? What I have here, 1 times anything is 1, so this has to go. Now, 1 over r raised to power n is 1 raised to power n, r raised to power n. 1 raised to power anything will always give you 1, because n will obviously be a positive number. So 1 raised to power 20, raised to power 21, raised to power anything will actually give me 1. So I don't have to write the n anymore. I can just write it as 1. So that's how I got 1 over r raised to power n minus 1. Of course, minus 1 here. Now, 1 over r here, this was on its own, minus 1. All right, I'm sure we all agree with what we have here. So let's go on to find the LCM. I want to be solving for the right-hand side alone now. Let me try and solve for the LCM, and let's see what we're going to get there. The LCM of this will obviously be r raised to power n. And then if we try and ask ourselves the question, we'll be having 1 minus what? 1 minus r raised to power n. Now, this is for the top. Now, we have another one under which we can also find the LCM as r. R goes in r, we'll be left with 1 minus r. All right. So I'm sure you all agree with what we're doing. So let's quickly, now we can write 127 over 64 is equals to, look at what this is going to turn to. We have 1 minus r raised to power n. Let me write this a bit clearer so that we don't have to. So we have 1 minus r raised to power n over r raised to power n. Now we had divided by, I'm turning this to this symbol, 1 minus r over r. All right. I'm sure you all agree with what we're doing right here. So let me try and dissolve the right-hand side. So I can dissolve this right-hand side to give me 1 minus r raised to power n over r raised to power n times r over 1 minus r. Okay. Now, I'm sure you are all following what's going on here. It's step by step and you will get your answer. So I can go on now to do something. I can, I want to bring this, of course, this can be rearranged. Look at the way I'm going to rearrange it. I'm going to have, of course, 127 over 64 is equals to 1 minus r raised to power n over 1 minus r times r over r raised to power n. I've not done anything other than just rearranging the form, because you can see now that wherever I have, I just put this all over this and this all over this. That's still very much permissible when we're dealing with mathematics, because that's okay. Now, this is where I want you to pay real attention. Are you seeing something already? I'm sure you can see what's going on here. Can you see that what we have here, this particular thing, is actually what we had here, which was our equation one? I don't know if you can see that. This was my equation one. I eventually did not rub it off. Can you see that this r raised to power, okay, I think I used, did I use a different, it looks like I used two different, I used two different, I made use of two different sum while solving this. I was supposed to, okay, just hold on. All right, so if you look at what we have there, we can see that we are dealing with, I think we can make a, sorry, I'm trying to trace the error. Uh, I'm trying to trace the error. It's looking like we had a mistake when we were doing a LCM. Right, I'm still with you. I'm trying to figure out. Uh, I think there's something going on here. We are supposed to get the very same answer. I'm thinking the LCM had a bit of an issue. This particular answer, we're supposed to get this same thing. So this is looking like the negative of it. Of course, I'm sure you know we can revert this, and this will be minus 127, but I really want us to get 127. It's You know what? I'm going to investigate this. Probably in the meantime, let me drop a particular question so you guys can keep on going on with that. I'm going to come back to this in a few seconds. All right. This is the question I would love you to solve. Just give me a few seconds. I want to investigate this LCM part. I'm not sure the right thing was done there. So let me clean up this place and just write something for you to tell me whatever you got there while I investigate this. All right. Okay, I think we can still do. There's a question I have here that has to do with sequence and series. The question said, for an arithmetic series whose first term is 2 and the common difference is 3, find the sum of the first 11 terms. For an arithmetic series whose first term is 2 and the common difference is 3, find the sum of the first 11 terms. All right, we're going to get this question in like some few seconds. Just give me. That was one of the questions I wanted to solve. Oops. Sorry, guys. We're actually on point. We're actually on point in that particular question. Sorry for this thing. We're actually on point. I think everything we did was perfect. This is just what's happening that I needed to have told you guys. Look at what's going on here. We'll come back to that question I gave you. Let me show you exactly what's going on here. This thing is actually the same thing as I was saying. One thing that was supposed to happen was, you see this thing here, let me prove to you that these two things are actually the same thing. 1 minus r raised to power n over 1 minus r is the same thing as r raised to power n minus 1 over r minus 1. You may be wondering, why is it the same thing? Look at it. If I decide to put a negative value, a negative sign here, that means if I say minus r raised to power n minus 1, of course, I do the same thing here. When I put in a negative sign, I'll be permitted to write 1 minus r raised to power n. If I do the same thing here, if I bring out a negative sign, I'll be permitted to do 1 minus r. I don't know if you can all notice what I'm doing right here. And we have 1 minus r raised to power n. This is minus 1. This is plus rn. This is minus 1. This is plus r. So you can see this and these are the same thing, because at this particular instance now, minus will cancel minus. So you can see that this and this are the same thing. That was what was happening right here that was about to confuse us. So this and this are the same thing. So what you have to do now is to fix in the value of 127 right into this place. All right. So I really thought we had an issue with the LCM. So if you, sorry, I'll come back to the question I told you, but let's try and complete this one. We're almost done. So obviously from here, I can write 127 over 64 is equals to no more this now, because I told you this and this are actually the same thing. That's what I actually proved here. That'll be 127 times r over r raised to power n. Actually, I think this is actually like, was this a theory question? This is one of probably 2023 past question, and you can see how technical this is. This is the reason why I told you guys that you have to get exposed to questions. This was one of the questions that you were expected to solve in one of the years, the past years. So looking at what we have here, you can see that we are dealing with something more solvable now. I'm sure you know if you divide both sides now by 127, you will get, of course, if you divide both sides by 127, that's multiplying by 1 over 127, multiplying by 1 over 127. 127 cancels 127, you'll be left to 1 over 64 equals to, this cancels this, you'll be left with r over r raised to power n. All right. Now, if you see what we have here, you can see that I want to see if you can look at what's going on here. Can you tell me, can you prove to me that this is actually equals to 1 over r raised to power n minus 1? This value we have here is actually equals to this. Now, if you can see what's going on here, this is the same thing as 1 over r raised to power n divided by r, which obviously will bring you back to right? Can you see that what we have here is the same thing as this? So I can rewrite this r raised to power r over r raised to power n as this particular function. So instead of writing r over r raised to power n, I'll be having it as 1 over r raised to power n minus 1. So 1 over r raised to power n minus 1 equals to 1 over 64. All right. And I'm sure you guys can solve from here, because understanding the law of indices, I'm sure you know that this is the same thing as r raised to power n minus 1 equals to 64. And if you go on to of course, you know r raised to power n minus 1 is the same thing as r raised to power n. I hope I'm not too fast for anybody there. So we have r raised to power n equals to 64r. Now, if you decide to put this particular, what we have gotten here, into equation 1, I'm sure you guys are feeling the heat of this question. And this is the reason why I said you have to really practice a lot, because the exam coming up is an A-level exam. So r raised to power n here, you fix that here. So you obviously will have 64r minus 1 over r minus 1 equals to 127. So all I did was, where I saw r raised to power n, I'm substituting 64r. I saw r raised to power n here, so I substituted it as 64r. All right, so you go on to make your cross multiplication here. So you have 127r minus 127 equals to 64r minus 1. So this will be 127r minus 64r equals to 126. All right. You see, when I saw this particular question, I wanted you guys to also feel, you know, this is from all what you have learned on sequence and series, look at the question I was examining for students. It's quite technical, I understand, but this is a direct pass question, and that's why you have to solve more. R here equals to 2. So we have been able to get the common ratio, and getting the common ratio obviously gives us a right opportunity to get I can easily now go on to get, I can get my n, because I was told to find the common ratio and the value for n. All right, looking at what we have here, this particular equation, I was told that r raised by n minus 1 equals 64. So if I fix in my r as 2 there, I'll be able to get my n value. That means I will have 2 raised to power n minus 1 equals to 64. 2 raised to power n minus 1 equals to 2 raised to power what? 6. So n minus 1 equals to 6, n equals to 7. All right? You guys, I'm really laughing at you guys. You see, this is A level. This is A level. Sincerely, I understand your frustration with this question. It's really technical. This is probably the most technical question I've seen on sequence and series A level JUPEB. This is, I must be very honest with you, it took a lot of you needed to be patient, you needed to move right. So you know what, let's just move to another question. I hope you get the understanding of this. I can come back to you later, but I don't want us to spend too much time. We have more questions to solve. Maybe I should not have started with that. I thought that was good for good for the night. Yeah, this is, I could tell you the past question so you can go on to check it out yourself. It's a past question. I saw it and decided to let you guys feel the heat also. All right. You know what? I have another question, and this next one is also technical. I will be honest with you. This is a past question also. It's okay. It's this one next one I'm going to give you also. It's a trigonometric question, and you have to pay attention. I think tonight is for technical questions. All right. I told you guys, when you are preparing for this exam, understand that nobody is going to give you, they wouldn't give you surface questions. Now, you may be lucky to see a few of them, but some of the times they bring out questions like this. Your comments are making me to laugh. Sincerely, you have not seen, you will still see more. This is A level. This is why, you see, we try to balance things up. So we'll solve some few non-technical, just a simple one, but also understand that there are lots of technical questions. Before the end of this class, I would love to show you, I will tell you the particular past question so you can go out and check it out yourself. But let's quickly solve this next question because of our time. This one is also a bit technical. If you are not knowledgeable enough, you may not be able to solve it. It's a theory question, a past question. Look at the question right here. The question said find tan 7 pi over 12 using the known value, the known values of tangent of pi over 3 and pi over 4. Just, I told you guys last year, that was what happened to them last year. They saw a question that was more than the ability. But I'm trying to get you guys to be prepared for any kind of question. So imagine you are done with learning sequence and series and you see a question like what we just solved previously. Of course, that's the way it used to be. So you have to be prepared and be ready to solve greatly. All right. Now look at this question we have. Look at this question we have right in front of us. We are told that we should find tangent of 7 pi over 12 using the known values of tangent of pi and over 3 and pi over 4. Do you guys have great understanding on how to solve this? Because this is one of those questions you have to patiently understand. Just so you understand, because of time, I'm going to walk you through it very quickly. Now, look at what they told you. They said you are supposed to find, this is what you're supposed to find, tangent of this. And they said you should not just go on, if I'm sure if they didn't write this additional quality to it, most of you will want to use your calculator and you will say pi is 180. You will say pi is 180. Then you say 7 times 180 over 12. Then you say tangent of whatever you have. I'm sure that will be the approach many of you would want to really move through. But they gave you a condition and said using the known value of tangent of pi over 3 and pi over 4. That means any other route you pass without using these two values, you would be marked wrong, even if you get the right answer. All right? So you have to follow the process. The process says you must use the known value of tangent of pi over 3 and pi over 4. So how do we solve this? Number one, we have to realize something. And we have to change our, we have to change our 7 pi over 12. This 7 pi over 12, we have to change it in such a way that it will replicate these two values. So how do we do that? Now, I'm sure you agree with me that 7 over 12, I can write 7 pi as 4 pi over 12 plus 3 pi over 12. I'm sure you agree with me that this is agreeable, like this is okay. Because if this and this are the same thing, this is going to add up to 7 pi over 12. And if you go on to examine this, 4 pi over 12 is actually the same thing as pi over 3 plus pi over 4. Are you seeing something already? That we have been able to change 7 pi over 12 to pi over 3 and pi over 4. The way we did that is what I just showed you here. So I went on to say my 7 pi over 12 is 4 pi over 12 plus 3 pi over 12. And then when you go on to, of course, you can see that 4 goes here 1, 4 goes here 3. And 3 goes here 1, 3 goes here 4. I'm back at this place. Now this is much more comfortable because I'm seeing particularly what I was told to use. All right. Now that means if I'm told to find the tangent of 7 pi over 12, then that means I can decide to write it rather as this: tan pi over 3 plus pi over 4. I can go on to write this. All right. I can go on to write this because 7 pi over 12 now, I've written it as pi over 3 plus pi over 12. Now, I'm sure you guys understand that when you have a question like this, this is a typical example of what we call it compound angles. Compound angles under trigonometry. So this is a great example of what we call compound angles. So we have to go on to make use of our compound angle formula. Now, this is the reason why I told you guys to note all your compound angles, because you'll be needing it. Imagine you had a question like this. I'll tell you the year. I think I have to be writing the year and the particular question so that you guys will know that this is not just from a different place. This is directly from a JUPEB past question, an A-level past question. So if you're able to come here and you don't know your compound angle formula, you won't have anywhere to go. So you have to bring out your compound angle formula here. And I'm sure if you remember the compound angle formula, we are told that tan A plus B is equals to tan A plus tan B over 1 minus tan A tan B. Any mistake in any of these signs will give you a wrong answer. So you have to be careful of your signs. All right, now let's go on. Now that we have known our compound angle, let's go on to let's try and find. Don't forget, this is the compound angle we're trying to address, tan pi over 3. We're trying to address tan pi over 3 plus pi over 4. Don't forget that. So we can go on to use this now, the compound angle. This will be equals to tan pi over 3. Of course, A here is representing pi over 3, and then tan pi over 4. Everything over 1 minus tan pi over 3, then tan pi over 4. All right, you can see exactly what we have to do now. This is why you must know your compound angles, because it's really coming in handy at this point. Okay, so what do we have to do next? I think this was a 4 marks question, by the way. All right. Now look at something going on here. Don't forget, you're not expected to go on using calculator to press this up. You have to, as much as possible, make use of what we call special angles. What is pi over 3, everybody? I'm sure you know what pi over 3 is. Pi over 3, don't forget, when you see pi, you're talking about radians. So when you see pi, you're talking about 180. So pi over 3, obviously, is 180 over 3 and gives me a value of 60 degrees. And pi over 4 gives me a value of 45 degrees. So essentially what we're looking for tan 60 and tan 45. So do we go on to press our calculator for this effect? Of course not. You don't need to have a calculator for this. You need to remember your special angles. Your special angles goes like this. You have 1, 1. You have to be able to draw this triangle. So 3. And right here we have our 60 degree. So if I'm going to find my tan 60, I'll be having tan 60 being equal to opposite. That will be so 3 over adjacent. That will be 1. So tan 60 is the same thing as so 3. All right. What about tan 45? Tan 45 will be tan 45. We use our special angle also. Our special angle, we have like 45 degree. We have 1, 1, so 2. So tan 45, that's opposites over adjacent. That'll be 1 over 1. That means tan 45 is 1. So now we can go on to solve this. This is tan pi over 3, which was tan 60. Tan 60 is so 3. This will be so 3 plus what's tan pi over 4? That's 1. That's tan 45, which is 1 over 1 minus tan, what was pi over 3? So 3. So 3 times 1 times 1. So I'm sure you agree with me if I wrote it like this. They're just rewriting it now. 1 plus so 3 over 1 minus so 3. All right. Now, this is good. This was our answer, but we can never leave our answer in this form. I'm sure you guys know why we cannot have this written like this, because this is the derivation of what we call an irrational number, because the root, the denominator is actually having sorts. So we have to go on to rationalize. So you have to quickly rationalize before you make your conclusion on this being the final answer. So you have to go on to rationalize this. So let's try and rationalize this quickly. I'm sure everybody here can do that. 1 plus 3 over 1 minus 3 will be equals to, of course, what we have to do is multiply this by the conjugate of the denominator, which is 1 plus 3. And of course, I'm sure you can see that when you have something like this, this will be 1 plus 3 plus 3. Then we have 3 times 3, that will be 3. Over, this obviously is difference of 2 square, because this is what happens when we have different of this. So this will be 1 square minus 3 square. All right, we are trying to rationalize 1 plus 3 is 4. That will be 4 plus 2 3 over 1 square. That's 1 minus 3 square is actually 3. So we're left with 4 plus 2 3 over minus 2. So we can break this down as 4 over minus 2 plus 2 3 over minus 2. We'll be having minus 2 minus 3, which gives me my final answer. Are you still interested in writing JUPEB exam after all this? All right. I think it was nice for us to deal with some of these questions, because there's no way we want to escape them. So let's run quickly to let's run quickly to functional mapping. We have 2 questions, also past questions. Let's quickly solve them, and if we still have time, we solve. Probably we still have more questions unsolved, but we may not be able to exhaust all of them. But let's move as we can. All right. So this question, I hope I was not too fast for anybody in the audience. I'm sure you guys were able to flow with me. You have to understand you're writing an A-level exam, so it has to be, you have to be very you have to be ready for a lot of technical questions. You can't escape it. I don't think there's a way to escape it. All right, look at this question quickly. You are told that given that we have x 3x minus 8, and you are told that x is a member of real numbers. So you are told to compute f inverse of minus 2. So this one will probably ease you up for the night. At least you don't have to have a night full of technical questions. I'm sure this one is not technical at all. So this should relieve you a little bit. Oh, somebody said I was a bit first, sir. Okay. All right. Now, let's quickly try and solve this. We have, of course, when you see something like this, given that x, this means that your function is given as 3x minus 8. All right. They said x is a member of real numbers. We should compute, that has to compute f inverse of minus 2. All right. F inverse of minus 2. How do we go about this? How do we go about this? Well, the very first thing, before I continue, if you have not liked this stream, please do so quickly. If you have not clicked the like, the thumbs up, give this video a thumbs up. All right. So we were saying something around trying to find the inverse of this before I went on to talk about giving a thumbs up. All right. Let's see how we're going to solve this. Of course, this is probably the simplest question you ever see in any past question. Any question has to do with functional mapping is probably very simple. I think you guys should rock it easily. So let's see what happens here. You're told to find the inverse, but you were not told to find the inverse of x. You were told to find the inverse with an argument of minus 2. So obviously, I'm sure you can realize that you cannot give just the answer for f inverse of x. But you know what? You have to go on to find, let's first find f inverse of x first. Let's find this. Let's find this first. So now that I have f of x equals 3x minus 8, the very first thing I want to do is to change. Don't forget, I gave you 4 different steps in order for you to solve any question on inverse functions. The first thing you have to go on to write, you rewrite as a linear function. That means you change your f of x to y, 3x minus 8. Then the next step is that you have to go on to wherever you saw y, you're fixing x there. Wherever you saw y, x, you're fixing y there. So wherever I saw y, I'm going to change it to x. Wherever I saw x, I'm going to change it to y. All right, that's step number 2. Step number 3, we have to go on now to find and make y the subject of formula. To do that, I want to cross my 8 to the other side. Then I want to have my y equals to x plus 8 over 3. Good. And then the last step, which is the 4th step, is for me to go on to change my y now to f inverse of x. I think I taught you guys well, right? So I don't think it should be a problem for anybody right here. Now, what do we go on to do now? We're formed for the inverse function for x, but we have not gotten the real answer we're told to get. So for us to find f inverse of minus 2, I need to go on to fix in minus 2 as an argument into this inverse function. That means that we have minus 2 plus 8 over 3. And this will give me what? 8 minus 2, that's 6 over 3. I got an answer of 2. All right, I told you this was probably the simplest question you will meet ever. So I understand if, so let's see another question quickly. Let's see another question so that we can, I'm really hoping that we can exhaust a lot of questions today. I really felt we should be, but that very first question, that technical question was quite long, and it took a lot of energy. So I hope we can pick back tomorrow, but let's see where we can get to for tonight. Given that f of x is equals to 1 minus 2x, and gx is equals to 1 plus 2x. Now we're told that x is a member of real numbers. Of course, that is represented by the symbol, the Greek symbol that looks like R. You are told to find FOG minus GOF. All these are direct questions from past questions. You are told to find FOGX minus GOFX. All right. How do we go about this? Well, the very first thing you need to know is that FOGX is the same thing as writing F then G of X. Of course, I'm sure you know that. So wherever I saw, this was my F of X function. You can see 1 minus 2x. Wherever I had X before, I'll be fixing my G of X there. So 1 minus 2, normally I would have written X if I was going to write my F of X. But now that I'm trying to find FOG, I will be fixing my G of X function. That will be 1 plus 2x. All right. This will be 1 minus 2. 2 times 1, 2. Then 2 times 2, that will be plus 4x. 1 minus 2 gives me a value of minus 1. Oh, sorry. This is going to be minus because minus 2 is here. Minus 4x. All right. I'm sure that was perfect. Now let's see GOF. GOFX will be G, then f of x being the argument. Now this is my G function. So I was supposed to write 1 plus 2. I was supposed to write x, but wherever I saw x now, I'll be fixing the function for f of x. So I'll be having 1 plus 2x. All right. So this will be 1 plus 2 plus 4x. This will be 3 plus 4x. All right. Now, the real question was that we're supposed to find this minus this. So that will mean, obviously, we're going to be solving minus 1 minus 4x minus 3 plus looks like our f of x is actually 1 minus. Oops. 1 minus. So here we're supposed to have a minus. Here we're supposed to have a minus. That'll be 3 minus 4x. All right. So this will be minus 1 minus 4x minus 3 plus 4x. Minus 1 minus 3 will give me a value of minus 4. Minus 4x plus 4x will give me a value of 0. So therefore, my final answer will give me minus 4, negative 4. You see how nice this can be? You see how nice these questions are? So I gave you a question and then I didn't solve it because I was trying to solve that first question. Let's try and do that one very quickly. That very first question where I said the first term is 2 and the common difference is 3. So I'm sure some of you did it. Let's do it together so that we can be sure we are done with that. So I told you, I said for an arithmetic series, whose first term is 2. For an arithmetic series whose first term is 2, for an arithmetic series whose first term is 2 and the common difference is 3. The common difference is 3. We are told to find the sum of the first 11 terms. So this was the question I gave you while I was trying to solve that question. That very first question I was giving us a little complexity. I'm sure you guys would like something like that in your exam. Now, you're told that we had an arithmetic series. Please always pay attention to this word arithmetic series or geometric series. That will always inform you on the direction to take. So you are told now that you are dealing with an arithmetic series. So obviously, this is different from that of a geometric series. It said whose first term is 2. That means I know that my A here is 2, and the common difference is 3. D is 3. We're told to find the sum of the first 11 terms. So to find the sum of the first terms of an arithmetic sequence, it's quite different from that of a geometric sequence, and it's given as this. I think I've given you this formula when I was dealing with sequences and series. And of course, in this case now, my n was 11 because I was told to find the sum of the first 11 terms. So n here is equals to 11. So to find S11, I'll be having 11 over 2. Then 2 times my A here is 2 plus 11 minus 1. My difference is 3. So I have 11 over 2. Then I have 4 plus, this is 10 times 3. That's 30. So I have 11 over 2 times 34. And I'm sure you know 2 will go here 1, 2 will go here 17. So I'll be left with 11 times 17, which is 187. So guys, you can see how this is, all these are past questions. Everything I'm solving tonight, every single one is all past questions. So these are the kind of questions, you can see there's a difference between this question on sequence and series and the first one we solved. Now we're going to close up the night with one question on MI. I just hoped to do that because you guys fumbled in the last test I gave you. And I'm really hopeful that it wouldn't repeat itself if that happens again. Because all the effort plays on MI, and you guys are supposed to do better. So I picked the question from the past question. This is also a past question on mathematical induction. And we are told is quite a very simple one. Of course, everything on MI is actually simple. I don't know why you guys are struggling with it. But again, for mercy's sake, let me try and solve one question. Just one question tonight on MI, a past question. So for those of you that don't even understand what to do at all, this could give you a very great understanding. And if you're still having issues, you can go on to watch the videos that we had on mathematical induction. MI is probably one of the most simplest topic you guys are doing. Very, very simple. It has no complexities. It has fewer complexities. It's very straightforward, and it's one of those parts of mathematics where it's very rigid. You just have to keep doing the same thing, and you keep every question you're giving, it's the same step. You don't have to change anything. It's the same thing. You keep doing the same thing over and over again. So this was the question. Probably 2021 or thereabouts. I'm not very sure of where I picked this from, but it's between 2020 and 2023. So you're told that you had something like this. So this is how the question this is how the question was given. Prove by induction that 1 plus 3 plus 5 plus ... plus 2n minus 1 equals to n squared. Now, so that you don't ever get all this confused with all these things, let me quickly address something. The meaning of this is that they are saying, while you are adding numbers, like this, when you are adding numbers like this, the sum will always give you n squared. This is what it really means. That means if I decide to add the very first term, the very first term obviously is 1. So 1 will be 1. When I say very first term, I'm adding the first term. That means in this case, my n was 1. If I decide to say I want to add the first 2 terms, my n there will be 2. If I say I want to add the first 3 terms, my n there will be 3. On and on and on. So if I'm adding the very first term, that means my n is 1. Now, to confirm if that was correct, if I go on to put, of course, n was 1, so 1 plus 1 is 1. So there's nothing. 1 plus, sorry, 1, I didn't say, sorry, I said 1 plus 1 is 1, not that. What I meant is 1 plus nothing is 1. Since the very first term is 1 and there's no precedent, so I stick to that being 1. So while on this left-hand side, if I decide to try to do the addition of the very first term, I got my sum to be equals to 1 because 1 plus nothing is 1. Now, on the right-hand side, on the other side, if I decide to go and put my n as 1 into this n square, what I will get is, if n was 1, of course, n square will be equals to 1 square, which is 1. So obviously, this worked. That when I was adding the first term, it gave me n square. Now, that was clear enough. Let's try and do for when I'm adding the first 2 terms. In that case, that means n was equals to 2 because I'm adding the first 2 terms. Now, if I do that manually from this left-hand side, that will be 1 plus 3. That gave me my value of 4. All right, that means 1 plus the first 2 terms, 1 plus 3. Now, but n is equals to 2. Don't forget because I'm adding the first 2 terms. So on this other side, my n, of course, if n now is 2, that means n square will be equals to 2 square, which will be equals to 4. Can you see it conforms to each other? So you can see it works. All right. Now, let me do for when n was equals to 3. That means the meaning of n equals to 3 means I'm adding the first 3 terms. I'm adding this plus this plus this. In that case, I'm having 1 plus 3 plus 5. That will give me a value of 9. All right. Now, let's confirm that if this was correct or not. Let's go on to fix. Of course, n is 3 in this case now. Put in n as 3. So if n equals to 3, that means n squared will be equals to 3 squared, which will be equals to 9. All right. You can see that all these are perfect. All these are perfect. Now, this is what we call our base step. This thing we just did is what we call our base step. All right. This is the base step. So there's the next step. I told you this thing it follows a rigid process. The next step is what we call the inductive hypothesis. Hypothesis is when you are making a guess or making a claim or something. So since we have seen that it worked for when n was 1, it worked for when n was 2, it worked for when n was 3. So we have to just go on and say it's going to work for when n was equals to k. So we're going to assume that this same thing, it is true. That this is true. It is true when n is equals to k. That's the next thing. We're going to assume that since it worked for 1, 2, 3, it's going to be true for when n was k also. It was true for when n was 1, when n was 2, when n was 3. So it's going to be true for when n equals to k. That's what we're going to assume. All right. So if that was the case, if this was actually true, that means we'll be having 1 plus 3 plus 5. Don't forget, n is now k. So we'll be having plus dot 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 plus 2k minus 1. And of course, since n is k, this of course will be changed to k squared. This is what we call inductive hypothesis. Now, the last step, which is the proving step, which is the part where we now want to go on to now confirm. You know, they said we should prove by mathematical induction. That last step is now the main step, and we must always do it. So this very, you know, I was saying something, if you guys remember that, if you are even the worst person in mathematics, the base step and inductive hypothesis should be able to be done by anybody. You're proving this, then you're assuming this. That's basic. So the major thing where some people could now have issues, depending on your ability to now solve mathematics, is in the proving step, where you now want to prove. So, but these first two things, these 2 steps should be able to be done by everybody easily. You just go on to confirm first, then you go on to assume. Now, how do we prove? Now, we want to prove that it will be true for n equals to k plus 1. I'm not doing so much of explanation on mathematical induction today, but I've already given you people a good analogy on how to understand this thing. Probably you have to go back and watch the video on mathematical induction, and then you will get that analogy there. But for this class, we just want to solve this. Now, we have proved for we have assumed that n equals to k is true. So let's try and now prove that for the next one after k, which will be k plus 1. Of course, the next step after k will be k plus 1. Let's prove that for that k plus 1 is actually also going to be true. So what do we have to do? If it is true for k plus 1, this is what it means. Pay attention now. 1 plus 3 plus 5 plus dot 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 plus. Now, before you go to k plus 1, don't forget you will have to get to k, because k comes before k plus 1. K is the figure, the step before k plus 1. So you have to go on and write for the k step. That will be 2k minus 1, then plus the next one, which will now be for the k plus 1. You can see the way I wrote it. So this is how you do it. So you don't skip any step, you would always get your answer. Now, if you do this, if it's actually true, now let me write this in red ink. If this thing on the left hand side is true, now I want you to be able to differentiate what we are doing. I can go on to continue solving, and what I must get must be this. This next thing I'm writing by this side here is not part of the equation. It's not part of it. This whole thing you keep solving, but this is what everything must result to. If it was true, it must resolve to k plus 1 square, because Of course, if n was k plus 1, that means when you fix in n as k plus 1, you'll be having this. So the meaning of this is that go on to solve for this left-hand side. If this particular thing is actually true, everything you get on this left-hand side must result to what you have here. So this and this are not together. You want to confirm that the left-hand side is actually was equals to what you have on the right-hand side. So what do you do now in order to solve this left-hand side? Very simple. From this place I highlighted now, I can see that this was all this. Of course, the k when n was equals to k. So rather than writing all this long thing, I can just write k squared because I was told that 1 to this place was equals to k squared. So I just write k squared now plus, of course, I can open this. This will be 2k plus 2, 2k plus 2 minus 1. All right. And now I have k squared plus 2k plus 1. This is what I got on my left-hand side. No, this is what I got on my left-hand side. Now, let's see, is it the same thing as what we have on the right-hand side? The right-hand side said k plus 1 all squared. Let's see what this was. This is, of course, I told you how to open this already easily. So this is k squared plus 2k plus 1. Can you see? It got the same thing. So I have proved by mathematical induction that it is actually true because I was able to prove for the base step, then I assumed in the inductive hypothesis step, and then I went on to prove that for n equals k plus 1, it is true. So solved. It's that simple. Once I'm able to prove that left-hand side equals to right-hand side, I've successfully solved the question. So that's everything about mathematical induction. It's nothing to be afraid of. You're not supposed to have any form of issue when it comes to mathematical induction. But the best way to get along with questions like this is to solve more questions. Expose yourself to more questions, which is one of the things I would always endeavor to do. If I see more questions around mathematical induction, I will still endeavor to bring them for us so that we can all solve. Now, of course, as you can imagine, we did not solve all the questions we had for the night, but we have to stop here at this time because we would continue from here tomorrow. So, of course, we started polynomial classes today. We were able to do a lot, and an assignment was given. I would love you guys to ensure you solve the assignment before 6 o'clock class tomorrow. We're meeting by 6 p.m. tomorrow for the polynomial class. It will last for about 1 hour or thereabouts. And then by 9 p.m., we'll be concluding this weekend's tutorial. And I really hope we can be able to solve a whole lot of more questions. And you guys, you have to do this. You have to really make this work. You have to make this A come out because all this is for that. So you guys have to do whatever it takes. So when you're done with things like this, you can go on to research for more questions. And if you want me to solve any question, you can forward those questions to me on my personal WhatsApp, and let me try and bring it for everyone to solve. Make sure you put in your best. Polynomial classes tomorrow now, we have a lot to talk about. We'll be talking about the remainder theorem, the factor theorem, and every other thing around polynomials. So you guys should ensure you're very much ready for tomorrow's class by 6 p.m. Yeah, I'm still your host. All right. Make sure you do your best and don't leave the rest, please, because there should not be anything left. So put in your best and do whatever it takes to make this happen. All right, guys. It's a beautiful night. By the way, the very first question, I probably would, who knows, probably tomorrow would talk about it again. What do you guys say? Probably we should talk about tomorrow's, the question we solved initially. Probably we'll do that tomorrow, probably so that we can make, maybe we should solve it because it's actually a question we have to know. It's very simple, but you just have to be patient. No. I can't solve one more question. I'm literally out of that space right now, so I can't solve one more question. All right. So, guys, thank you very much. I wish you all the best. Enjoy the night. Bye bye.